Hey, AP Statistics. So continuing on with section 6.1, in the first part, we looked at discrete random variables and calculating their mean. Of course, the next step is the standard deviation, measuring variability and variance as well of a discrete random variable. Remember, variance is just standard deviation squared. With the mean as our measure of center for a discrete random variable, it shouldn't surprise us that we'll do the standard deviation for variability. And here it is. Boom. The standard deviation of a discrete random variable measures how much the values of the variable typically vary from the mean. Suppose that x is a discrete random variable with this probability distribution. So we've got, again, those possible outcomes. These are numbers. And then the probabilities of each of those probabilities should sum up to 1. And that the mean, and that mu sub x is the mean of x, that random variable. So they have the variance, and then, of course, the standard deviation, we're just going to take the square root. But the variance, we can basically take each outcome, each possible number, minus the mean that we calculated in the last formula, square it, and then you multiply by the probability. So kind of similar to the weighted, it's like a weight, the variance is kind of like weighted in that way as well. It's because we don't have like a total number or anything. It's times that proportion. And you do that for each one. You then take x2 minus the mean squared times its proportion. x3 minus the mean squared times its proportion. And you do that for all of those. And so if you want to shorten that formula up, you can do it with the sigma right there. And this is also on the formula sheet. This stuff is the standard deviation of x is the square root of the variance. So just throw a square root over that big long mess, or basically right there. And that is your formula for the standard deviation. All right, so probably best to see it in practice. Again, with the Apgar scores, we're going to calculate and interpret the standard deviation of x. So we had our mean from before for this. It was 8.128. And so then we are going to take each outcome, 0 minus 8.128, square it times that probability. 1 minus 8.128, square it times that probability. And so on until we get through the whole list. That will be variance, and then we'll take the square root to get standard deviation. So there's our variance, 0 minus 0.828 squared times that probability, and all the way through to the end. This is a typo. They did the same thing again. That should say, all the way through to 10 minus 8.128 times 0.053. And that's the variance. Take the square root, and you have the standard deviation. And so if we want to interpret that, that is a randomly selected newborn baby's Apgar score will typically vary from the mean of 8.128 by about 1.437 units. It's the typical distance that will end up being from the mean. And that is standard deviation, so we can calculate the mean and standard deviation for discrete random variables. All right, so then the next thing we have are continuous random variables. So discrete are when we have those specific outcomes, like they're like whole numbers usually. You technically could have like defined fractions, but the idea is over a range of values, there's a finite number of possibilities. Continuous is that it can take any value over an interval on a number line. So between any two numbers, there's an infinite number of possible values. That's the idea of continuous random variables. So things like time and weight and height and those measures are continuous. Whereas discrete is things like number of heads or number of wins or something like that, or number of siblings, right? You don't have like fractional decimal type stuff for that. It's, there's defined possibilities. So how you find probabilities for a continuous random variable, the probability of any event involving continuous random variable is the area under the density curve. So we bring density curves back, and this is from chapter 2. Directly above the values on the horizontal axis make up that event. So you have to do it over a particular range of values. Remember, with continuous random variables like the normal distribution, the probability of any exact outcome is 0. We always have to go between values to get an actual probability or proportion for that range. So the probability distribution of a continuous random variable, in this case y, we've got the height of this density curve, we've got this uniform density curve, is the area below that density curve between those values. So if we want to go from 3 to 7, this shaded area underneath that density curve represents that region. And in this case, if we wanted to calculate that probability, we would take 4 times 1/9, since this is just a nice rectangle, so we can calculate the area of that. But we'll do that in this next one. Selena works at a bookstore in the Denver International Airport. She takes the airport train from the main terminal to get to work each day. The airport just opened a new walkway that would allow Selena to get to the main terminal to the bookstore in 4 minutes. She wonders if it would be faster to walk or take the train to work. Let y equal Selena's journey time to work in minutes by train on a randomly selected day. The probability distribution of y can be modeled by a uniform density curve on the interval from 2 to 5 minutes. Find the probability that it will be quicker for Selena to take the train than to walk that day. All right, so it's kind of a lot going on here, but it's y is a random variable. It's the time that it takes on the train. So it takes in random number. It is a uniform density curve, so we're dealing with one of those flat lines. And so we're going to draw this out. We got range from 2 to 5, and so we kind of got to calculate 2 to 5. The height of the density curve ends up being, since this range is 3, it ends up being a height of 1/3, so the entire area underneath that density curve is 1. Now, we're in particular interested in the area below 4, because remember, there's a way to get there in 4 minutes, so we want to know what's the probability to be there faster than that. So we want to be less than 4, and so that's why we're talking about this portion of the curve, and ultimately we're going to calculate the area of that shaded region. And so that's going to be the probability. And a lot like back when we did proportions in a particular range for these density curves. So basically, formula for a rectangle, base times height. So this distance here is 2 times 1/3. 2 times 1/3 is 2/3. And so that is the probability. You could convert that to a proportion or a percent, like 66 or I guess 67%. And that's the probability that y will be less than 4. So there is a 66.7% chance that it'll be quicker for Selena to take the train to work on a randomly selected day. We'll also do this. So we'll focus on uniform density curves. But there's another density curve that we'll use a lot more, actually. Other density curves other than these two we'll stay away from because they need calculus. But and technically this one even needs calculus, but we've got our calculator that can do some of these things for us, and we've got the table as well. So we're going to use normal density curves as well and figure out probabilities in certain range. The heights of young women can be modeled by a normal distribution with mean 64 inches and standard deviation sigma is 2.7 inches. Suppose we choose a young woman at random and let y, again, random variable, equal her height in inches. Find the probability that y is between 68 and 70. Interpret this value. And again, I'll remind you that in a continuous distribution, it doesn't matter whether we say less than, like the equal to actually doesn't matter because that line has no area. So this is what we're talking about here is just this range from 68 up to 70. So we're just doing the area under the normal distribution between those. This is going to be basically a lot like what we did before, only we're calling it a probability now instead of like a proportion of a population. So we could do this if we wanted to, like use like the table. We could do that. We could actually type this straight into our calculator, but we'll do that second. If we want to do this in the table, I'll remind you we could convert those into z-scores. Z-scores are standard deviations from the mean. So you could convert the 68 into a z-score, 68 minus 64 over 2.7, which was our standard deviation, to figure out that that is 1.48 standard deviations of the mean, above the mean. Looks like it's like 1 and almost a half of a standard deviation above the mean. And then the other one, 70 minus 64 over 2.7 is 2.22. So it's 2, so 1, 2, and a little bit more, about a fifth of a standard deviation more above the mean. All right, that's the z-scores for both of those. And so we could look both of those values up in our table A, our normal table, and it gives us the area below. So we would actually look at the area below this one minus the area below that one. So if we did that with our table, if you look up 2.22, you should see 98.9868, and then subtract away the area below this one to get the area in between. Although probably easier than that is to use technology, go normal CDF from... You could do the z-scores, lower to upper, right? That lower z-score, that upper z-score, leaving the mean is 0 and standard deviation is 1, and you get the exact same probability, or approximately the same. Rounding might throw things off a bit. Or we could have done it with the original values instead, typing in the lower bound as 68, and the upper bound as 70, and then typing in the actual mean and standard deviation. So then finally, to interpret that value, that 0.0561, the probability that a randomly selected young woman has a height between 68 and 70 inches is about 0.056, and that is the probability we get a young woman in that range.